so we're going to start with number 20. Oh, right away I noticed what units does my answer have to be in? Megajoules. Mega, big M. Megajoules. There will be a bunch of people who forget that and run into that problem. We had it in, what was it, 18 in T-Block today, because they wanted the answer in minutes. And that evaded some people. All right. Human power, produced standard output about 0.3 horsepower. Crossing this channel. Yep. How much energy does the pilot expend during flight? How many candy bars does the pilot have to consume? Okay. All right. So, the root of this is that power is the rate energy is used. That's a U, not an O. Right? So, the longer, wow, spelling is not going well today. Longer the energy is used, the more energy will be used. And you can probably put some other little statements in there, right, about, oh, the more power you need, the faster energy will be used and all that. But that's the core essence, I think. Good? Okay. So, from our handy-dandy equation sheet, we're looking at power and we're looking at the amount of energy or the amount of work done, kind of the equivalent thing. So I'm going to use energy over time, change in energy over change in time. Don't forget that change part. That's important. Power is the change in energy over the change in time. And now really it's just kind of getting things into the right headspace. So power output, 0.3 horsepowers, which would be 0.3 times 746 watts, to try to get it into watts, right? Because we want to work in the metric units. So over here I'm just going to do a side note of power equals, for me, 0.3 times 746. And then let's see, I go back to my problem. It took 2 hours and 49 minutes. See, an hour is 60, that's 120, so that's 169 minutes. So delta T equals 169 minutes. Oh, but I don't like minutes. What do I like? Seconds. So I need to make that into seconds, which would be 169 times 60 seconds. Now I'm in my nice base units of watts and seconds. Because that gives me energy in what units? Joules. Right, joules. And then I can always convert that to megajoules. Right? So for part A, all I'm doing is plugging in, right? 0.3 times 746 watts equals delta E over 169 times 60 seconds. It's all for delta E. Yep, all I would do is look at my equation sheet and go over here to this nice little prefix chart and notice mega means 10 to the 6th. So that means there are 1 million joules in a megajoule. So whatever answer I got, I would divide by 1 million. Is that clear? Good? Excellent. Second page of the equation sheet, right-hand side, under the title prefixes. All right, and now, how many 280 calorie per bar candy bars would the pilot have to consume to fuel up for the flight? Note that an additional calorie is equivalent to 1,000 calories as defined in physics. And 1,000 calories equals 4,186 joules. Express your answer as an integer. What does that mean? Huh? Beyond that, yes, the whole number. So this is really just conversion, right? So for part B, I have an answer in joules. I want to convert it, so I multiply it by the number 1 joules per calorie, 4,186. That gives me a value in calories, and then I can figure out from there how many candy bars I have to eat, right? By taking that answer, multiplying it by the number 1 in cal per candy bar. 280. All right, 17. Which has a fly walking up, straight up a window pane. This is one of those that says part A, but doesn't have a part B. Power output of a fly walking straight up a window pane at 2 centimeters per second. 2 sig figs include appropriate units, and they put them in, and notice the units they put in milliwatts. Remember, if you don't want to answer in milliwatts, you can just get rid of the little m and answer in watts. Right? You can modify the units, and it's smart enough to know whether or not it's correct. Just like, like Lauren, like the last one, you didn't have to answer in megawatts if you didn't want to. You could have changed it to watts and answered. All right, so 17 here. Power is the rate energy changes. The faster you move against, that's spelled wrong. It wasn't. It does look wrong. Isn't that wrong? It looks wrong. Against a force, the quicker your energy changes. Thus, more So the faster you move against the force, the quicker your energy changes, thus more power. Remember we talking about car engines, top speed, those type of things? So I'm actually going to put a little diagram to start off my how, just to make sure that I'm clear of this. So I have my happy little fly. The weight is going to be going downwards. The fly is going to be moving upwards. Right? At a constant rate or accelerating? At a constant rate. At a constant rate. So technically, there's also going to be a force on the fly in that direction. So those two balance out. But the work that I'm doing is against gravity. It's going into giving the fly gravitational potential energy. Okay? So I'm going to jump to my equation sheet again and grab another form of power. And power is force times velocity. And it's actually, there's a dot in there, but don't worry about that. And so the amount of power that I need to use here, that's what they're asking for, right? Yeah. I have a 1.5 gram fly. Its weight is going to be mg, right? Should I use that mass in grams? No, what should I have it in? Kilograms. So my mass, so this is going to be mg times v. The force that opposing me is my weight, is the weight of the fly, whatever speed it's moving at. Its mass, therefore, is going to be 1.5? Yeah. 0.0015 kilograms. I'm assuming this fly is taking place on the Earth because I don't know flies on Mars. And then I have its velocity, which is 2 centimeters a second. Should I use it in centimeters a second? No, what should I have it in? Meters. So that would be 0.02 meters per second. And that will all come out to some answer in watts, because kilograms times newtons per kilogram is newtons. Newton meters is a joule. Joules per second is a watt. All right, number 19. Power up a flight of stairs. Review of that lab that we did. Except now they want you answering horsepower. So you climb up a flight of stairs in 10 seconds. Your mass is 72 kilograms. We assume that you do this on Earth. So what type of energy do you gain by going up the stairs? What type of potential? Gravitational potential. So I would put that in your Y. Right? You gain grav TE by going up the stairs. The power is the rate you gain energy. I know this is going to be a shocking equation.
Is this going on YouTube?
Yep. Right? And then, of course, you also have from our equation sheet right? Now it's just substituting in because you know everything. Right? Let's see, they said 72 kilograms. Assume that you're on Earth because I haven't known you to be anywhere else. They told me you went up 3 meters and you did it in 10 seconds. What units is power going to be in? Watts. And then, of course, they want your answer in horsepower, so watts times 1, which would be watts per horsepower, and it's 740 something, 746 again, hasn't changed. Gives you an answer in horsepower. And Ms. Martin will be so proud of you that you can convert units. I'll let her know. All right, so number 7, and then we'll get to number 16. 7, I'm going to let you answer part A on your own because, quite frankly, I answered B and C, and then answered part A. Right? So your brakes cause a constant deceleration of this regardless of how fast you're driving. Not really true, but let's assume it. And back at the stopping distance to the initial speed of this. So let's see. This is 7. The faster, the longer distance to stop, since the change in velocity, otherwise known as the acceleration, change in velocity is greater, but the acceleration is constant. And I might even add in it takes more time also. Right? To change anything, it takes some amount of time. If you're moving and you're changing your motion, you're also going to move some distance during that time, or some displacement. That's just kind of truths of life that you got to kind of imbibe, right? So if I'm moving faster, it's going to take more time for that acceleration to change my speed, because there's more speed to change. Therefore, more time is going to take a longer distance. Then we couldn't say. Your brakes, are not a constant deceleration. But it can get complicated. So we'll try to stay simpler. Now, a lot of people, we look at our equation sheet about accelerations, and we notice a lot of them have time involved here. But the problem doesn't say anything about time, right? It just wants to know stopping distance. And so, to use our equations with time, we might need to figure out the amount of time, and then we can figure out what the distance is and everything. Or, luckily, we have a relationship here that involves just the velocities, the acceleration, and the distance. So we So there's a couple ways to do this. We could use that, or we could say, okay, let's find the amount of time, and then we'll find out how far you went in that amount of time. That's a completely legitimate way to do it. I'm not going to because it's more work. And why do more work? If I have a day for understanding, I don't need to. So I'm going to use v final squared equals v initial squared plus 2a delta d. And in case A, the 11 meters per second, I know in both cases, what does it mean to stop? What's my velocity? 0. So I'm going to have 0 meters per second squared equals, my first time it's 11 meters per second squared plus 2, 3.9 was it? Yep. Meters per second squared. And that's actually negative 3.9. And then just delta D. Otherwise, I get an imaginary number, which is good. And then I just do the exact same thing, but for 22 meters per second. Without even doing the math, because the velocity is squared, is it going to be twice as far or 4 times as far? 4, because I've got that doubled squared. So. All right, number 16. Remember, the Y for this one needs to be a force diagram, right? So you always square yourself on good old terra firma when your weight is this, an elevator apparent weight is, ooh, what measures apparent weight? Or what's the other word for apparent weight? Normal force, right? That was in the lecture. So what they're really saying is that on solid ground, your weight is this. In an elevator, your normal force is this. What's the magnitude of the elevator's acceleration? Does your weight change when you accelerate? No, but your normal force can, right? What would you have to do to change your weight? Reduce gravity, increase gravity, get rid of part of your mass, right? Cut off an arm, a leg, torso, something. That would decrease. And you could sew something on to increase. Yeah, we can talk about Z Nation later. So, force diagram, let's see. There's you. We'll put you standing on a scale. Maybe we'll give you a head. We'll give you an extra arm too. Why not? You're going to have your weight down. Normal force up. Ooh, which one is bigger? Your normal force in this situation or your weight? No, look at the problem again. Let's look at the problem again. Your normal force is smaller. 400 is less than 500. Okay, you got that? Okay. So I should probably amend my drawing and make this one longer. So, if your weight is bigger than your normal force, which way is the net or total force going to be? Down. So which way does your acceleration have to be? Down. Is normal net force and acceleration always in the same direction? Not net force. Total force. Alright, so that should be your force diagram. Or better. So I'm going to go down here. I'm going to grab 2 equations from my equation sheet. I'm going to grab Newton's second law. It says sum up all the forces, multiply the inertia by the acceleration. And I'm going to grab our good old friend, the definition of weight. Right? and they tell me that my weight is 535 newtons. On Earth, so I could figure out, whoops, kilograms per newton. What am I losing my mind here? Oh, nice, we have flex, don't have to go anywhere. Right, and you can figure out your mass. Well, why do we want to do that, Mr. Congress? Just because you can. Abby, you got that?
Yeah, I was
I gotta get it.
Get out of here. I don't want to see you again. All right, now, some of our forces. How many forces do we have in that diagram? 2. Which direction do you folks want to call as positive? Up?
No.
Not even any thought. Up. Down?
Down.
Okay, so we're calling down as positive. That means I have F sub G, which is positive, minus force normal, equals M times a positive A. Well, that works. 535 newtons minus 485 newtons equals the mass I just found out from over here times A. Solve for A. And it'll end up being in meters per second squared.